All right, problem 36 off the math subject GRE practice test. Getting into a little, I guess, topology or set theory is what's going on here. S is a non-empty subset of the real numbers. Which of the following is necessarily true? So in problems like this, what you want to think of are some different types of subsets. So make sure you consider open subsets, closed subsets, connected versus disconnected. Um, Infinite versus finite. Infinite. What else? Empty and the entire set are things that generally you'll want to consider. Although in this case, it tells us that it's a non-empty subset of R. But generally speaking, you'll want to consider the empty set as well. And then so you kind of think up some examples in your head, some common counterexamples. And once you get an idea of the properties of those common counterexamples, you can typically answer questions like this. So what I'm saying is I'm going to answer this question. I'm going to give you counterexamples for 4 of these 5. But those counterexamples won't be that specific to this question. They'll be counterexamples that'll serve for lots of other similar questions, assuming you encounter something like this. So the first one, for any 2 elements in my set, there exists a continuous function f mapping 0, 1 onto my set, where f of 0 is one of those elements and f of 1 is that other element. This is not necessarily true. This could be a false statement for lots of different. I think all I need is to make this guy disconnected in order to have this false. But an easier example is what I will let maybe all in this column. This will be my S. Should that S be 0, 1? Note, this is not the interval from 0 to 1. This contains 2 elements, the element 0 and the element 1. So S is, maybe I'll call that 0, and T, I'll call that 1. So what I'm saying is that f of 0 equals 0 and f of 1 equals 1. So I'm thinking about my function right here. Goes through this point, and it goes through this point. Is there a way to draw this to keep things continuous, to draw this without picking up your pencil? Well, you might think so, except that S, my image here, only contains zeros and ones. So what I'm saying is the height for every single value between 0 and 1 here must be either 0 or 1. So I got a whole bunch of zeros, and then at some point I jump up here and I got a 1. And maybe it jumps back and forth a few times, who knows? But something like this is certainly not a continuous function because it jumps. It has to at some point jump from 0 to 1 at least once. So this right here would not be my answer, and here would be a counterexample for it. B, for each element not in my set, there exists an open subset containing that element that's not in my set, such that the intersection of my set and this open subset is empty. Okay, that's a lot to wrap your head around. When you see this idea of elements not in sets, often your set being opened or closed will be enough to come up with a counterexample. In this case, I think any open set will do. This open set will certainly do. Suppose that S is all elements from 0 to 1, not including 0 and not including 1. What this is saying is for each element not in my set, so I could let U, that's a poor looking one, U be the element, I don't know, 1, for example. 1 is certainly not in my set because my set is everything between 0 and 1, not including 0 or 1. If I think about an open subset around 1, so you got some little ball, might be really, really small, but it contains 1, and then some numbers that are slightly less than 1 and some numbers that are slightly more than 1. How many, I don't know. It would be very, very few, but there's something there. The intersection of this set and this set will not be empty because this open subset necessarily contains a number that is less than 1, and any number less than 1 is contained in S right here. So this would not necessarily be a true statement. It turns out that C is a true statement, so maybe I'll go back to that in a little while. D. The set of all elements not in S. So I don't know what S is yet, but S is some sort of set. The set of all elements not in that set, such that there exists an open subset they call the open subset capital W. And little w is some element inside capital W, and capital W is an open subset. So what I'm talking about is the set that contains all little w's. And what is a little w? Well, a little w is an element of a capital W, and a capital W is just an open subset of R such that the intersection between W and S is empty. So that set, a very confusingly defined set, that set right there is a closed subset of the real numbers. I think that'll be false, and I think I can use this same counterexample, 0, 1. So this open interval, all the numbers from 0 to 1. What is the set of all elements such that there exists an open subset? So what would that contain? Maybe, where do I write this? Over here. If S is this guy, then this set is going to contain a lot of elements, all the elements from negative infinity all the way up to 0, but not including 0, and I'll explain why in just a sec, and then all the elements from 1 up to infinity. I think that this set will be this guy if this right here is S, and this thing right here is not closed, it's open as a union of these two open sets. This right here is open, not closed. An easier way to see that it's not closed, its complement would be everything from 0 to 1, including 0 and 1. And the only way a subset is closed is if its complement is open, and everything from 0 to 1, including 0 and 1, is not open. Anyways, how do I justify this? Well, if this is S right here, I'm thinking about including a lot of elements that are not in S. So I certainly don't want the numbers from 0 to 1. So I'm going to include a lot of elements that are not in this set right here. But I can't include 0 or 1 either. And I can't include 0 for the same reason as I kind of came up with the counterexample up here. I can't include 0 because an open subset around 0 would not leave me with an empty intersection between S and that subset. So I can't include 0. I can include anything smaller than 0 if I want, but not 0 itself. So this right here is not a closed subset, so D is not necessarily a true statement. What about E? S is the intersection of all closed subsets of the reals that contain S. There's probably a few ways you can get around this, but the one that I want to use, because it's a very nice counterexample to have, is the rational numbers, and maybe I'll take all the rationals from 0 to 1, for example. All the rational numbers, so this is S over here, I should have written it, fine. The rational numbers from 0 to 1. Is it true that this set is the intersection of all closed subsets of the reals that contain S? No, because any closed subset of the real numbers that contain S is going to have to contain all of the numbers from 0 to 1. If you want to contain all of these, you must contain all the numbers from 0 to 1. The intersection of all closed subsets, so maybe I write this over here, the intersection of all closed subsets of R that contain S, in this case, that'd be everything from 0 to 1. That's not the same as S. S is the rational numbers from 0 to 1. The intersection of all closed subsets of R that contain S are all the numbers from 0 to 1. Because those two sets are not the same, this is not necessarily true. Therefore, E could not be my answer either. So by process of elimination, my answer must be C. You can talk yourself into C a little bit. So what's going on here is my set is made up of all the elements V that are in S such that there exists an open subset V of R. Little v is in capital V, and capital V is a subset of S. So take any set you want and think about all the elements that are in the interior of that set. They're in the interior of that set because there must be an open ball around the elements that are contained in that set. So what I'm trying to do is take some set S and think about the interior of that set S. Is that an open subset of R? Yes, that is. That's very true. The interior of a set will always be, oh, you got to be careful with those always. If it's finite, I think that's true. The interior of a set will always be an open subset. Even if it's empty, that would still be open. It's open and closed. So I think that's a true statement. In this case, it's certainly true. So C would be the answer to this question.